Hello, I'm Judith Hurwitz. I am the Cheif Evangelist here at Geminos. It's great to see you today. It is my great pleasure to introduce our speaker, who is Scott Cunningham. Scott is a professor at Baylor University, and he's also the author of the very popular book, Causal Inference, the Mixtape. And it's really my pleasure to have you and your cat join us for this discussion.
It's nice to be here. Thank you, Judith. This is my cat's. This is, I guess, a Zoom interview with cats walking around. Sorry.
Right. Well, you can never have too many cats. So let's start with sort of some of the issues around causality. It's getting a lot of publicity. Gartner has put causal AI and causal inference on their hype cycle, so a lot of people are starting to talk about it. And there are a lot of people that I'm hearing saying, well, wait a minute, isn't correlation good enough? I mean, we've been doing correlation for decades, and if you read, and we'll talk about Judith Pearl's book, but if you read his book, he talks about the debate going back, centuries, about the debates between correlation and causality. So maybe you can sort of address that issue.
Great. Yeah. So that's a common I think that's a common response that people have when they hear about causal inference. Is just, first it's a real jargony word, or a set of words, and people don't quite know what it means. And they think that it seems like it's probably unnecessary because we already have so much advanced statistical machinery that we use currently. So what exactly is the value added of this so-called causal inference? And I guess I would just say, I'll just sort of give an example of ways that, confusing things that tend to be happening at the same time, and then thinking that one of them causes the other, can actually lead to fatal mistakes. I'll just kind of, take it outside of the area of business and profitability and just talk about, life and death stakes. In the 1800s, there was a wave of fatal cholera epidemics that hit London. Tens of thousands of people died. And back then, nobody knew what caused cholera. The most common belief was that disease was spread through smelly air, through smelly odors. It was called miasma. And so the way that they were trying to deal, and it was very natural to think that. Why? Because, smelly air is oftentimes correlated with bacteria, especially in a place like, a rapidly changing city like London, that was going through the Industrial Revolution. But their focus, on trying to save people from these cholera epidemics was just to continue to focus on making the air cleaner. And because it was really correlated, with these deaths. But the problem was they had open, really poor sanitation and open cesspool areas. And when people would die from cholera, their excavations from their body would get into these open areas that smelled really bad, and it would go back. The bacteria, which they had never seen before, would go back into the Thames River. And then they would drink from the Thames River. And so even though yes, if you had run any regression, you had done any kind of systematic, predictive modeling, you would have always found a highly strong correlation between the smelly odors and the deaths, even in some sort of spatial analysis. And it would have always been wrong. And so, not being able to separate, out when is one thing just simply happening, coincidentally. Two things can happen for lack of a better word, you can even move away from correlation. You can just say lots of stuff happens systematically for coincidental reasons, But if you don't know the difference between coincidence and causality, you will make fatal business decisions, because every time a firm is wanting to know, pretty much almost always, when you dig really deep and you talk to managers and you talk to product managers and you talk to executives, why do they want to know a correlation? Deep down, if you can just sort of like, kind of get them with their therapist and get deep down as to why they want to know. Why do they want to know? Because they want to take one of those variables that is correlated and they want to change it to get the outcome that they see it correlated with, right? So if they see that something is systematically correlated with revenue, well, they want to move that thing to get more revenue, right? And that's a causal question. That is not a correlational question. That's the thing, is that correlations are just in the toolbox of causal inference, but correlations are bigger than just causal inference. They're used for all kinds of stuff. They're used for classifying things and identifying patterns, but not necessarily to make policy decisions. Mm-hmm. Policy decisions at the public level or the private level, policy decisions are always causal questions. If I do this, will this thing change, and by how much? And right now we are having a moment. We are having a moment with causal inference. It's both happening in industry, but the Nobel Prize was just given in 2021 to David Card, Hito Embens, and Josh Angrist. And Hito Embens and Josh Angrist won it for causal inference. They won it for work they did on causal inference. And so, at the moment, both in the area, just kind of in the broad area, I think people are realizing that in science and in the social sciences, sometimes you can't run A/B tests. This kind of thing is that in tech, they have been for decades doing randomized controlled experiments. There have been more randomized controlled experiments done at Microsoft than there have probably ever been done anywhere in medicine. Just probably far more RCT, randomized control trials, have been done in the last 2 years than was ever done before tech in the history of humanity. But there are many questions that no one will run randomized experiments on. There's lots of critical business questions where it is viewed to be just simply too costly, too risky, or just unethical or impossible to do that. And yet they still want to know, should they do more of it? So it's a really important area.
So obviously AI and machine learning, big, huge discussion, many tools out there. So is causality just another way of saying AI and ML?
No, I mean, it's, artificial intelligence and machine learning, in my mind, are very sophisticated areas bridging computer science and statistics for uncovering very complex patterns in very unusual, very, very historically unusual data sources, that unlike anything we've ever had before, even including sounds and media. So there's all kinds of stuff that we can do now with artificial intelligence and machine learning that are not just causality, but sometimes they are. Recommendation systems have elements to them that are clearly causal in nature. If I recommend this to you, will you do something? Right? That's a causal question. What the recommendation system that's based on the artificial intelligence, that might be purely something algorithmic. But if you're asking yourself, if I do this, will this thing change? It's still causal. So increasingly, artificial intelligence and machine learning have been moving closer and closer in conversation with one another, looking at what they can learn from one another. And so they're not in tension. It's more like, the way you pair a great meal with a great bottle of wine. Right. And then the meal is causal inference, artificial intelligence, right? You don't put them in tension with each other. You just try to find how both of them can work together to answer very important, difficult questions. And so they're different, but they absolutely can be complementary if you know how to make them be complementary.
Yeah.
And that
So
can't be done naively.
Yeah. So there's another question that keeps coming up. A lot of data scientists the theory is that if I have enough data, enough of the right data, then I just apply that to my algorithm and I come out with an answer.
Yeah.
In terms of causality and causal AI, there's an approach that says maybe you should model your problem first, because if you don't know what problem you're trying to solve, what's the Wizard of Oz, any path will get you there, or
Right.
maybe that's Alice in Wonderland.
Uh-huh.
So the question is, do you model first? Do you just go and collect all the data that you think is appropriate?
There's no way to get around it. All of causal inference requires human beings, having prior knowledge about the problem at hand, having expertise, or what's oftentimes these days just called domain knowledge, experts, right? Why? Because, when you're not working within the realm of a randomized control trial, you're having to make comparisons between two groups of people, two groups of situations, right? The thing that you get from randomized experiments is that in some ways it kind of like addresses this core problem in causal inference, which is, the core problem of causal inference is, so for instance, she's using an example. I have a PhD in economics and I have a certain level of happiness, right? Is my PhD responsible for my happiness? Did it make it go up? Did it have no effect? Did it make it go down? All right. Well, how would I go about answering that? Well, here's the deal. Here's what causality means in this modern scientific sense. Causality means compare my happiness right now, today, August 22nd, my happiness in a world where I have a PhD, to my happiness, August 22nd, 10:23 a.m., if I didn't have a PhD, right? That's what causality is. Causal effect of the PhD is a comparison between two states of the world. Only one of them happened, right? So therefore, causal effects of a PhD at my level, unknowable. I have no idea what the effect of the PhD was on my thing. So what do people do? They take groups of people that have PhDs and they take groups of people that don't have PhDs. They try to do a bunch of adjustments and they look for some gap between them and they say, that's the effect of the PhD. Well, it may or may not be. Because
there could be
there could be lots of other stuff. That's the thing, is that none of those people are me. None of those people are me. And so the hard work of causal inference is not coding. It is not writing programs. It is finding appropriate counterfactuals for people in large groups such that the bias associated with any comparison is minimized and known to be minimized theoretically, right? Because at the end of the day, I will never know what my happiness would be had I not gotten a PhD. But we can get progress on that with large groups of people where we model with using expertise knowledge about the nature in which PhDs occurred in these groups of people and didn't grow with these groups of people to do adequate comparisons, and if so naive artificial intelligence, that's being used to answer causal questions, it's just going to be a seemingly very sophisticated version of the old correlation causality question. That's all it's going to be. It's just going to be a fancier version that's going to be overconfident, and not enough people in the room are going to know that the emperor doesn't have any clothes on.
Yeah, very well said. So let's talk about sort of explainability and bias detection.
Yeah.
Those are two really critical issues that a lot of people are talking about.
Yeah.
So how do you see causal AI and causal inference impacting our ability to explain what's going on in these complex systems and to avoid even unintended biases? You don't even know that there's a bias there?
Well, that's deep. That is definitely deep. I mean, I think that, explaining a causal effect versus believing a causal effect, are almost kind of like two separate things. So you could imagine like a team of people in a firm, right? A team of data scientists, all of whom have similar training, all of whom have similar background. And what they need to do in order for the team to believe that they have identified a causal effect, is based on a certain kinds of training and skill and human capital like contained within the team. But then if they have to go communicate that finding to someone not in the team, it gets to be really hard. And because the person they're communicating with may not be a data scientist, wasn't there for any of the conversations, didn't look at any of the data. And so you've got to find a way to have like a common language, to say that this is a causal effect. And there's a lot, and getting into that we're at the beginning of that, we're at the very beginning of that. And so I think that, within if you want to call it a field, causal inference is you can call it a field. Causal inference is more like, stuff that a lot of people do. If you want to call it, it's more of like stuff, because you could even say, in medicine, they're doing causal inference, because they're running randomized control trials on vaccines and stuff. So, everybody's been doing it for 100 years or longer. But I think what I would say right now, there's certain tools and certain kinds of ways that we now know can be very effective to explain causal effects that cuts through this issue of correlation a lot easier. And one of them, I think, is the use of Judith Pearl's directed acyclic graphs. The directed acyclic graphs have many, many, many valuable pieces of value for people engaged in causal.
So define what those are for people who don't know that.
So the directed acyclic graph. So Judith Pearl is I believe the 2014 or 2011 Turing Award winner in computer science. It's like their field's Nobel Prize or their field's medal. And so he's a legend. He's a legend in computer science for both his work on artificial intelligence, but also his work on developing this very elaborate probabilistic based system of causal inference. My understanding of the history of it is it was rooted in the work he was doing on artificial intelligence and came kind of naturally out of it. Pearl is just a very original thinker. He approaches, he doesn't come from economics, which is my background. He doesn't come from the social sciences. He was building things up to solve practical problems within computer science, and so he managed actually to end up in the same place that many other fields kind of have come up, both in economics and the broader social sciences in general. But because he kind of approached it in his own way, there's lots of unique value with what he does. And there's lots of very original insights that he has found that you don't find in the other areas, And so one of the best things that he did, and I don't exactly know why it had to be graphical, because a lot of the graphs are, he developed an entire mathematical notation for causal inference that was ultimately graphical, meaning it was based on graph theory. It was pictures, nodes with arrows, called directed acyclic graphs, where the arrows are causal and the nodes are variables. And if you could commit using your basically being an expert in an area, presumably means you do know something about, how things are connected to each other. You have your instincts, you have prior scientific literature, you have your own observations, your own experience, your own models, your own field's contributions. You have the ability to sort of say, well, the reason people go to college is because their parents went to college. And the reason they also went to college is because they had the money to go to college. And the reason they went to college was also because they got a scholarship. and because of this, and you can start to sort of build out a story. You can call it a story, right? You can call it a story. Calling it a story makes it almost seem, smaller in nature, but really, so much of science storytelling. It's about building models of the world that are abstractions of a very complicated system.
Based on knowledge. I mean, you
Based
have
on
to have
knowledge.
knowledge in order to do that.
Yeah, you have to have knowledge before you can do that, right? And so what Pearl showed is that if you are willing, and maybe this is part of his Bayesian background or something, but if you are willing to use the knowledge rather than just like pretend it's irrelevant, use the knowledge to actually tell the story about the system itself, then it actually allows you to identify, that's what we call it in economics, to identify causal effects between variables without the randomized control trial.
Mm-hmm.
Right? You can develop a model, right? But it's not like a model, like, there's all kinds of models out there. And in some ways, what Pearl means by model is very different than what I think people sometimes think. Like when they think of the model, I'll take one in economics, like a model of monopolies, right? Like monopolies, they're one firms that charge prices, et cetera. It's like, well, that theory of model, the theory of the monopoly, it has nothing to do with any particular situation. Pearl's was different. It was not a theory of the monopoly. It was the theory of the situation that you were in. It was a theory about the actual situation that you were interested in studying. And if you were willing to kind of like, think about that complex system, then Pearl actually provided a set of mathematically coherent, statistically coherent, procedures that could identify the causal effect that you might not know, right? Mm-hmm. And not have to run the randomized experiment. And that actually, so that's really like very powerful, very, very valuable. But the thing about it that I think is underappreciated by many people kind of in it, they like use it, but like as an outsider, for me, especially as an educator, the thing that I find so powerful about Pearl's notation is that it's pictures. Everybody that looks at those pictures, you could talk to a person whose first language is not English, and I am speaking English, and they don't speak very good English, and they have no stats background. I could show them that picture, and within 15 minutes, we're on the same page. We're at least on the same page. Right?
Which is very important when you're putting together hybrid teams of data scientists, knowledge experts, data experts, in order to really come to
totally, absolutely. And the great thing that Pearl has also done is Pearl has, in a series of papers, as well as with colleagues and with students, shown that there is, even in these other so-called branches, you know how academia gets, it gets very clubby and cliquish, and people act like there's more differences than there are similarities. But Pearl has shown that there's one-to-one correspondence between a lot of these broader, areas of causal inference that we kind of associate with the Nobel Prize and the DAGs. They all kind of are based on the same fundamental reasoning, same fundamental philosophical reasoning of counterfactual based theories of causality, that PhD in economics and happiness idea. So, what makes it so great is that even that what makes the causal graphs so useful is that you can talk to other people that aren't in the team.
Yeah. But
what's nice about this artificial intelligence, and the other thing that's nice actually, is that Pearl is a computer scientist. The machine learners have been learning from him for decades. All this DAG stuff has been in the tech community for a long, long time. Right. So the building of causal inference on top of it is low marginal cost conceptually, right? Because they're already using them. So the fact that there's already been this willingness to embrace him and his work and his peers' work and this whole community that came out of this like UCLA and larger body of scholarship, and that it's been found to be so practically useful. That's the other thing. It's practically useful, right? He's building,
and it's also not starting from scratch. Okay, yeah. I got to get rid of everything I've done before, or everything I know, and now blank slate. So
exactly.
So it really builds on what data scientists and economic experts already know.
I think it does. I think it does. I think it builds on it. I think that it's a great bridge to the causal graphs are a great bridge into now learning more, because there's a ton of tools and there's a ton of techniques that are like spread over all these areas.
And a lot of open source as well.
Oh yeah, tons. That's right. And because a lot of this stuff, because all this stuff is not just heady, you know, borderline philosophical, right? You know, like who wrote about causality historically? It was David Hume, right? It was Aristotle. It was like, you know, Mill. It was philosophers, right? They're not writing code. They're not trying to answer, you know, if I like pass this policy, you know, will I, you know, retain more workers? Will, you know, will work from home increase profitability? Will it increase worker productivity, or will it reduce it? These are causal questions. Yes, work from home is a causal question. It's not a correlational question, right? People are, you know, and you can't use it. You can't just look at the fact that some firms are using it and some firms aren't, because that they're like, it's what we call in economics, it's endogenous. They're doing that for reasons that's going to create horrible, confusing correlations that mask all the causal effects. And so, you know, the philosophers, if you go back to the philosophers and read all this stuff, it's like very, very interesting. I find it interesting. It's not helpful. It's not helpful, like in the worldly sense of like, should I do this thing? Yeah. Well, that's what's great is like the world of causal inference now, it's like worldly philosophy, you know, because it's like, it's programmers, there's code, right? There's open source packages. There's open source packages in Python, in R, you know, there's tons and tons of examples of like learned ways of doing this to do it right, and as opposed to doing it wrong. Nobody has to reinvent the wheel. Nobody has to invent this stuff.
Great. Well, Scott, thank you so much. It's been a fabulous discussion, and people should definitely take a look at your book, Causal Inference. The Mixtapes is a great book and strongly recommended. And thank you so much for your time, and we'll be talking more.
Thank you. Nice talking to you, Judith.